In the previous video, we saw how to set up a delta-delta CT study using ExpressionSuite. Now, before we analyze the data, which we'll do in the next video, we need to examine a few quick quality control parameters. Let's see how to do that right now. Starting from the home screen, I'll select the study we just created and click Open. If we wanted to, we could add more experiments to the study or make other changes to the setup. For our purposes though, let's go straight to Run QC under the Workflow menu. We have 4 quality control sections to look at, starting with the first, Flag Summary. Much like the latest version of real-time software on most AB instruments, ExpressionSuite flags wells that it feels might be problematic. The software assesses numerous parameters in each well, including baselines, thresholds, passive reference levels, and so on. The entire list is here, along with lots of frequency data over to the right. To view these wells, we simply go to Amplification Plot under the Workflow menu, select a gene target containing flags, and look here in the lower right pane. So how does ExpressionSuite determine which wells get flagged? I click on Analysis Settings, followed by the Flag Settings tab. These are the default parameters for each flag. Look at the first one on the list, Amplification and Negative Control. Is now set whenever a no template control has a CT of less than 35, the well will get flagged. We have the option of changing that value if we wish. For some flags, we can even tell the software to automatically reject wells that fall outside of the acceptable range. Also, we may activate or deactivate certain flags depending upon which problems we want the software to monitor for us. Feel free to turn flags on or off as you wish. Just be sure to understand what each flag means before you tell ExpressionSuite to reject wells automatically. And if you'd like to know more about what a given flag means, just go under the Help menu, and under Contents, click on Flags, and now you get the full list. Just click on the one that you'd like to know more about. Okay, well let's go back to the amplification plot. As we click on each gene name, the corresponding wells appear. By the way, the y-axis of our amplification plot is in linear scale right now, which is different from the default view of log scale in the real-time software. So as a first step, I like to go under Plot and choose delta RN versus cycle. That's log scale. A few things to note about these windows. First, there's a handy mouse over feature that indicates which well a particular amplification curve belongs to. Second, if we select individual wells over to the right, only those curves will be visible. In order to see thresholds in the amplification plot, simply go to View, Thresholds. What should be clear is that regardless of the threshold settings in the original real-time files, they're being set in ExpressionSuite across all plates. This is important. We need consistency in the threshold across all of our data for a given assay. Now when we click on this gene, notice that all samples do in fact have the same threshold. Oh, also, the software defaults to using auto threshold and auto baseline. We're welcome to use these just as in the real-time instrument software, but we similarly have the option to switch to manual mode, and this is done under Analysis Settings and can be changed for the individual assays. We'll also need to reanalyze the data after making any changes to the analysis parameters. For a full screen view of the amp plot, we can click the double arrow icon like so. This is particularly useful for using the mouse over feature on specific wells. To go back to the original view, we simply escape. Similarly, we can draw a box around an area of interest, then click the magnifying glass with the plus sign. To return to the normal view, we click the Fit Data button. Let's say we have a well that we want to visually tag for our own reference. We can select it here and either go to Bookmark, Add Bookmark, or simply right-click and choose Add Bookmark. Until we delete it, that bookmark will be associated with the sample all the way down through the results. In the amplification plot, we can also color the bookmarks separately so that they really stand out. Bookmarks have no effect on the data. They merely provide a visual guide for wells of interest. We'll next go to the Samples tab. This is the same data as the previous view, except now it's separated out by sample instead of by assay. The Experiments tab similarly lets us view all data for one entire plate at a time. So really, all three of these tabs merely allow us to group and examine the same data in different ways. The multi-component plot, which we access by clicking here, shows us what each dye is doing in a given well at each cycle of amplification. We won't spend a lot of time on this topic since the utility of multi-component plots is covered extensively elsewhere. Just be aware that these plots, which are also part of the original real-time run file, are sometimes very helpful tools for performing either data or instrument troubleshooting. Finally, we have the box plot. This is a graph that helps us visualize the amount of variation in expression among either samples or, if we change the plot type, a given assay. We'll use the first graph option for this example. Holding your mouse over a box provides several potentially very helpful values. The solid box delineates the middle 50% of CT or CRT values, depending on which analysis method we used. The black circle is the mean value, and this black bar marks the median. The end lines here, known as the whiskers, are the minimum and maximum values, unless the data contains outliers that have yet to be omitted. Speaking of which, whenever there's a moderate outlier, we'll see an open circle. Open triangles indicate extreme outliers. This is probably the most useful feature of the box plot, visually indicating whenever we have outliers within a biological group. Switching the plot type, we see clearly that it's one gene, GH1, that's the big outlier. So the question is this something we expected? Perhaps GH1 is just a low-expressing gene and there's no issue. But one thing that does concern us is what we see back in the results pane under amplification plot. When we select just GH1, we see that for the pancreatic duct sample, the replicates aren't precise. This is something we often see with low-expressing targets due to something called the Poisson distribution. Basically, at very low concentrations of target, replicates often show poor precision. Not our fault. The question is, do we trust the data? And my own feeling is that once replicates start to spread this much, we may want to eliminate them. To do so, we'll simply select the wells as we've done, right-click, and omit. Finally, we reanalyze the data. To learn more about box plots or any of the other features in the software, go to Help, hit the Search tab, and type in your search term. Now, when you find your topic of interest, simply double-click on it. And that's it for quality control. In the next video segment, we'll perform an analysis of our study data. Please come back.